Hello everyone. In this video I am going to discuss about Q factor. Q factor is a dimensionless quantity and it is used in analyzing damped oscillators. It is like efficiency. So what are damped oscillators? An oscillator in which energy is continuously dissipated is called as damped oscillators. So there are many damped oscillators: LCR circuit, spring block system. In nuclear reactivity we have damping. So there are so many places damping takes place. So in all these damped oscillators, we can use this Q factor. It is not only derived for AC circuits, it is generalized one. So the basic definition of Q factor is average power stored by average power dissipated, and this is only for resonance. Now if you are using energy, we can write Q factor as 2 pi times of energy stored in one cycle by energy dissipated in one cycle, and this is again at resonance. So let's derive Q factor for LCR series circuit. Consider this LCR series circuit at resonance. At resonance we can write XL equal to XC and omega naught equal to 1 by root LC. Now in the left hand side I am proving Q factor by using powers, and the right side I am going to write Q factor in terms of energies. So Q factor equal to power stored. Either you can take power stored in inductor or you can take power stored in capacitor, because both will be equal. So I am writing I RMS square into XL. I am writing for inductor. You can write for capacitor also I RMS square times of XC. Since XL equal to XC, both will be same, divided by power dissipated. So XL we can write omega naught into L by R. So quality factor is, substituting the value of omega, we will get root over L by C into 1 by R. So let's try to derive same thing by using energy equation. So energy equation quality factor is 2 pi times, this is important, when you are writing energy you need to multiply 2 pi into energy stored by delta I. So what is energy stored in inductor? So energy stored in inductor is half Li square, half L into IRMS square. Now energy dissipated in one cycle. So we know power is IRMS square into resistance, this power into time period. So time period is 2 pi by omega naught. So this 2 pi and this 2 pi will get cancelled. So we'll get Q equal to omega naught L by R. So important thing is, when you are writing energy equation, Q factor is 2 pi times of energy stored by energy dissipated in one cycle at resonance. So both the things you are going to get the same one. Now what is the significance of quality factor? If you look at this energy equation, any damped oscillator, we pump energy to the system. So that energy is stored and some amount of energy is being dissipated. If delta E is tending to 0, that means whatever the energy is being pumped, it is completely stored in the system. That means the quality of that particular circuit or particular oscillator is very high. So whatever we are giving, that amount is being stored. But that is not going to happen in all the oscillators. Because of damping, there is some loss in energy delta E. So if you are able to minimize these losses or this dissipation energy, then quality of the particular circuit will be high. So larger the loss of energy, quality factor will be less. Lesser amount of energy loss, quality factor will be very high. So let's take one more interpretation of Q factor. So LCR series circuit in resonance, and I am drawing graph between average power and different values of omega. So I am changing the value of omega and I am drawing the graph. So the one which is drawn with the red ink, it is for resistance R. So first consider this red graph. So as you are increasing the value of omega, your power is continuously increasing. So power is increasing and it is reaching maximum value at omega naught. And as you continuously increase it, it will decrease. Again, it is becoming 0 at when omega is infinite. Now, I am taking 2 points where power is P by 2, P max by 2. P max I have taken as P, half of the maximum is P by 2. At half of the maximum, I have taken 2 omegas, omega 1 as well as omega 2. So, in LCR circuit, if at all the power, if it is less than P by 2, that is less than half of the maximum value, then it is insignificant. If it is delivering power greater than P max by 2, then only we can consider that particular circuit. If it is less than P by 2, it is useless circuit. So that's why I have taken 2 points with omegas giving us P max by 2. So this part of the graph is important for us. From here to here, the graph is important. Now, what I did is I have changed the resistance, keeping everything constant. L, C, VRMS, everything constant. I have changed the resistance. So when I am changing the resistance, my Pmax has been increased because power is VRMS square by R at resonance. As R is decreased, power will increase. So power has been increased. Now, if I take P by 2, I have taken this maximum power as P1. Half of the maximum is P1 by 2. I have drawn 2 points here with omega 3 and you can consider as omega 4. So you can consider this as omega 3 and this is omega 4. And we know one more thing, as resistance is decreased, quality factor will increase. The quality factor with the graph bluing is more compared to the quality factor of graph with red ink. Now the same quality factor we can also write it as Q equal to omega naught by delta omega. So this delta omega. So delta omega is nothing but difference in frequencies, angular frequencies omega 2 and omega 1. Otherwise difference in angular frequency where power is half of the maximum value. So this delta omega is called as bandwidth. So delta omega is called as bandwidth of this particular LCR circuit. And the value of delta omega is simply R by L. So I will derive this at the end of this video. So delta omega simply value is R by L. So Q factor is omega naught by R into L. So same thing, you are going to get the same thing. Now as delta omega decreases, quality factor increases, because in both red and blue graph omega naught is constant, whereas if you see delta omega, so delta omega for blue one is less compared to delta omega of red one. So as quality factor is increasing, delta omega is decreasing. So let's take an example to understand this quality factor in better way. So I've taken this two red and blue graph. In red one the resistance is more and in blue one the resistance is very less. Otherwise quality factor of second one is more compared to quality factor of first one that we have seen in the previous example. So now I want to use this particular LCR circuit. So I am writing this as LCR and this is LCR1 because the resistance is different. Let's say you are using this particular LCR circuit in sending sound with different frequencies. So I am writing here frequency 1 corresponds to some sound source S1 and this frequency corresponds to sound source S2, so on. And there is one omega 1 and omega 2. So these omega 1 and omega 2 corresponds to frequencies with power P by 2. So this is P by 2 and this is power P. and we have one more source S3 and corresponds to this frequency, S4, and there is a source S5. So these are different sources, S6, S7 and S8, similarly S9. So each and every source corresponds to different frequencies. Now if you are using this particular LCR circuit in transferring sound waves, so what happens is all the sources which is S4, S5, S6 and S7 as well as S8, they are inside your P by 2 to P range. That means all these particular frequencies can create power greater than P by 2. So I'm writing here S4, S5, S6, S7 and S8. So these are in between omega 1 and omega 2. That means they are going to create power greater than P by 2. I said if they are going to create power greater than P by 2, they should be considered. Now but all the S1 source, S2, S9, they are beyond P by 2 range. That means these can be ignored. Now if you pass the sound coming from all these sources through LCR circuit, output from S1, S2 and S9 will be 0 after passing through LCR circuit. Whereas you will hear sound from S4, S5, S6, S7 and S8 because their power is greater than P by 2. But you want to hear only sound coming from S6. Let's assume that you want to hear the sound only coming from S6. But how many sources are you listening here? Extra one, S4, S5, S7, S8. So these are unnecessary ones which are being heard in this particular LCR circuit. Now let's take the same thing for the right side one where quality factor is very high. So what I am doing is I am writing omega 3 and omega 4. So this corresponds to P by 2, P max by 2. Now I am taking the same sources that which I have taken in the previous one. S1, S2 here corresponds to this source, and S3 I missed here I think. So I guess S4 will be somewhere here. So I will have S5 in this region and S6, and similarly here S7, S8 and S9, so on. So this graph is not up to the scale. I just wanted to explain you about what is going to happen in both of the cases. Now look at here. Now here all the sources are generating sound, but S1, S2, S4, S7, S8, S9, all these are out of bandwidth. So these sources are out of bandwidth, so they are not going to create that much of output. So their power is less than P by 2. If power is less than P by 2, you can just ignore these sounds. So these sounds are not going to be heard in output. So what are the sounds that you are going to hear in the output? That is only S5 as well as S6. So in output you are going to get S5 and S6. Now out of these two circuits, which one is better for hearing only sound from S6? Obviously I would say second one, because there is no extra noise from other sources. Only S5 is there. Compared to here, we have total 3-4 different sources other than S6. So this is better for sending sound. So this has high quality. So quality factor is very large. So we can say that if quality factor is very high, then bandwidth of the particular circuit is very less, or sharpness of the circuit is very high. So bandwidth is very low, quality factor is very high, as well as sharpness of power and omega curve is very high. If you look at here, the graph is sharp compared to this graph. So if you have any doubt regarding quality factor, you can just comment below. In next video, I am going to discuss about quality factor in damped spring block system.